Let's talk in more detail about position, velocity, and acceleration here in chapter 2.2. We're going to say, let's treat time in seconds, just to be nice and metric. The position you would think would be called p of t, but for some reason physicists usually use s of t, so that's what we're going to use. Again, to be nice and metric, let's use meters. We often think of it as along a number line, like our car and bike example. There, time was represented by the animation of seeing the car move this way. But when we have to draw it as a static picture, we usually put time on the x-axis because that's kind of our independent variable in a physics kind of sense. And then we are kind of forced to put position along the y-axis, even though we're thinking the car is moving horizontally rather than vertically. So we've got time in seconds along the x-axis and position in meters along the y-axis. So it's kind of a number line but turned sideways. Velocity is the rate of change of position. That's the definition of the word velocity. And so in calculus terms, we say the rate of change by putting a prime or a derivative symbol on something. So if s of t is the position, s prime is the rate of change of that position. And then because it's such a common thing, we give it its own letter. We call it v of t. The units of the derivative of s would be units of y divided by units of x. So that would be meters per second. So that's what we get here. The acceleration is defined as the rate of change of velocity. So we get v prime as the rate of change of velocity, and it's such a common thing, we give it its own label, which is a of t. And then its units are the units of velocity, which is meters per second, divided by the x-axis, which units of the x-axis, which is time. And so it's meters per second, like how many meters per second are we adding per second that goes on? And then we often abbreviate that as meters per second squared, but sometimes it's useful to think of it as how many meters per second am I adding to my velocity per second. And then another specialized word is deceleration, which is just a short way of saying negative acceleration. A lot of times we don't like talking about negative values, so we turn them positive and then use a word to denote that it was negative. So if I say something is decelerating at 5 meters per second squared, that's telling me the acceleration is negative 5 meters per second squared. Cell actually means speed in Greek or Latin or something. So accel is the rate at which you're accumulating speed. Decel is how fast you're losing speed. So just a fun ancient Greek or Latin lesson there. So let's apply this to a case of cruise control in a car. Maybe not everyone is a driver at this point, and that's okay. I certainly wasn't at this point in my college career. Cruise control is part of a car that tells you, or that senses what the current speed is and then tries to keep it at some value you set. So you could tell the cruise control, I want to stay at 60 miles per hour, and then you can take your foot off the gas pedal and it will try to maintain 60 miles per hour even if there's a headwind or a tailwind or you're going uphill or downhill. So it's kind of handy on long car drives. There's something new called adaptive cruise control that tries to do cruise control, but then if the car in front of you is going slower than 60, it'll try to get to within like 2 seconds of the car ahead of you and then slow down to match the car in front so you don't go crashing into it, which sounds like a good idea. But for now, let's just do plain cruise control. And I was wondering, how fast do you lose velocity when you drop out of cruise control? So I was on a highway and my wife had a stopwatch in the passenger seat. So we went 60 miles an hour for 20 seconds, then I canceled cruise control and we tracked how fast the speed dropped. And in about 10 seconds, so from 20 seconds to 30 seconds, it dropped from 60 to 50. So go ahead and graph what's going on. So cruise control, our velocity was 20 seconds, was 60 miles per hour for 20 seconds. And then it dropped pretty much plainly to 50 by the 30-second mark. So go ahead, lay out an axis and graph the velocity. Pause the video, 3, 2, 1, pause. Okay, welcome back from pause. So the first thing to do is lay out what's going to be on your x-axis and y-axis. So here's how I envision the situation. We usually put time on the x-axis if we have time in the problem. And then we were cruising at 60 miles an hour for 20 seconds. So for the first 20 seconds, our velocity was just a flat line. It was always 60. Even though we were going forward quite fast, the velocity itself was staying constant. And then at time 20, we kicked it out of cruise control and it dropped to 50 miles an hour by time 30. And it was a pretty constant rate of decrease, so I'll just draw a line like that. So it was flat in this region and pretty much linear. We weren't tracking it in great detail in that region. So now let's draw the acceleration graph. So before I draw it, you should go sketch it on your note paper, lay out some axes, and then say what would the acceleration graph look like. Okay, ready? 3, 2, 1, pause. Welcome back from pausing. So let's lay out an acceleration axis. And we're actually decelerating here, so I'm going to need some negative possibilities. I'm going to use the same 20 and 30 to match up there. What was the acceleration during this period? Well, could you say I don't have any acceleration, so I just didn't plot anything? I would say we do have acceleration, but the acceleration is 0. So it would have an acceleration of 0. It's hard to do a plot with a value of 0 because the lines just plain overlap, so I'm being a little sloppy here. And then what was the acceleration from time 20 to time 30? Oh, we haven't talked about units yet. What should the units of acceleration be? Well, we said up here that they were meters per second squared, but that was in metric. Here, what's going on? Acceleration is rate of change of velocity. Velocity is miles per hour, and then we're tracking it per second. So units of y divided by units of x, the acceleration is actually in miles per hour per second. Miles per hour is kind of an abbreviation. Let's write it as miles per hour per second. So this is not miles per hour squared, and it is not miles per second squared. We've got different time units going on in the y-axis, in the x-axis here, and in the y-axis. So that's why I like writing the units of acceleration as meters per second, because it generalizes better to a situation like this. So what's the value of our miles per hour per second over here, where I'm dropping speed? Well, the slope right there, let's say, is 50 minus 60 over 30 minus 20. 50 minus 60 miles per hour, 30 minus 20 seconds. So I get negative 10 miles per hour in 10 seconds, which is negative 1 miles per hour per second. And that's not just the slope here, it's the slope there and there and there and there and there. So I have an acceleration value of negative 1 during that whole region. So let's put a mark on the axis here, negative 1. And what was the acceleration? Oh, we should label our axis here too. What was the acceleration right at time 20, that instant we dropped out of cruise control? Well, for there to be a derivative of this function, the values from the left and the right have to match. Here they don't match. So mathematically speaking, we would put an open circle here and an open circle there to say the acceleration just was not defined at that instant we hit the switch. Physically, you could argue in the like millisecond by millisecond category of like the cruise control computer turning itself off. You could argue for like a smooth transition between those two, but just from a simple mathematical model, if I've got a sharp corner there, then it doesn't have a single unique defined tangent line, so there's no slope of the tangent line we can talk about, and so we would have no defined acceleration right there. So overall, if I had to describe this acceleration curve, I could say a of t, well, it's got different things going on. So I'll do a piecewise notation. It was 0 for t less than, oh, not less than or equal to, strictly less than 20 seconds. It was negative 1 for t greater than 20 seconds, strictly greater than. And it was does not exist for t equals 20 seconds. We won't worry about what was happening out beyond 30 or before 0. So this d and e does not exist. And usually in calculus, we like smooth curves where the derivative exists everywhere. But in this case, and in a lot of physical situations, it's kind of easier to think about there was a sharp change there and the derivative just fails to exist. All right,